Hello dear students. So we had seen in the last few classes what are the strategies that are adopted for simple passive techniques as well as advanced passive techniques in the cold climate. Today we will continue with the warm and humid climate. In order to have a building designed as per principles of bioclimatic architecture, for future proofing with simple and advanced passive strategies, let us look at the passive strategies to be adopted in warm and humid climate. So, let us see quickly what defines warm and humid climate. So, warm and humid climate is characterized by high temperature and high levels of humidity throughout the year. There is no respite in this kind of a climate. So, the daytime temperatures can be consistently warm and hot throughout the year. It ranges from 26 degrees centigrade to 32 degrees centigrade. As far as the humidity is concerned, the air tends to have a high humidity level which stays above 70% and often reaches 80% or even higher, sometimes going up to 95%, making the place very sultry. Rainfall typically exceeds 1500 millimeters, evenly distributed throughout the year, but has a very distinct wet and dry season. So, warm, humid climates are conditions that are found in tropical regions near the equator. So, most of the places places having warm and humid climate are densely populated. These conditions create ideal environments for lush tropical vegetation, including rainforests and wetlands. Additionally, warm and humid climate are also at a risk of tropical storms, hurricanes, typhoons, and cyclones. Now, let us see what the Mahoney's table finally gives as design guidelines and planning guidelines for warm and humid climate. So, for Chennai climate, this is the guideline that the Mahoney's table gives. The orientation should be north and south with long axis along east and west. There should be open spacing for breeze penetration and there should be protection from hot and cold winds. The rooms should be single banked with permanent provision for air movement, and also the room should be double banked with temporary provision for air movement for certain months of the year. Opening sizes should be medium, ranging from 20 to 40%. The internal and external walls could be heavy. There should be heavy roofs with a time lag of 8 hours. This is the broad guideline that Mahoney's table gives. Now let us look at what the climate consultant gives as broad planning and design guidelines. So we saw what Mahoney's table is giving as a suggestion for simple passive strategies for a warm humid climate. Now here we will see, with the help of Chennai city, its climate type, considering it to be warm and humid, let us see what climate consultant suggests as simple passive strategies advanced passive strategies we will see by using simple and advanced passive strategies how much percentage of hours in a year can be made comfortable. We are not able to make all the hours comfortable, then what strategies, what active strategies should be used to make 100% of the annual hours or one full year to become comfortable. Now, we also know that the strategies for each month is bound to be different. I have already demonstrated this in the climate consultant software, how for every month the strategies are different. So strategies for each month is bound to be different. Just to show you how these differences happen, we will be analyzing the psychrometric chart for 4 solstice periods. That is, we will look at strategies for June, September, December and March. So for these 4 months, what strategies can be used, and if those strategies do not give 100% of the time to become comfortable, then what active strategies can be used to make these months completely 100% comfortable. This is what we will see. So, if we look at Chennai, for adaptive comfort, this is how the psychrometric chart looks. I have already told you, I have already taught you how to arrive at this. Now, once you arrive at this, this shows that if we also use plus ASHRAE Handbook 2005, then it shows that sun shading of windows alone will give 35.9 hours will be pushed to comfortable. Here we are looking at simple passive strategies for the month of March for a warm humid climate represented by Chennai city. Now for March month, in order to make the indoors comfortable, solar shading of windows will make the indoors comfortable by 36%. 267 hours which were actually uncomfortable will become comfortable just by shading the windows. Then by using adaptive comfort ventilation, 47% of discomfort hours can become comfortable. In total, 48% can become comfortable, but 52% would still remain in the non-comfortable zone with just simple passive strategies. So, for making the indoors comfortable for the month of March with just simple passive strategies, we can have good natural ventilation, which can reduce or eliminate air conditioning in warm weather if windows are well shaded. So we have seen already what shading means. We will use horizontal shading, which is sunshades. We can use vertical shading, our fins. We can use the egg crate device. We can use the egg crate device. Any of these shading devices as appropriate can be used if we want to shift at least 34% of the hours to comfortable zone. Then we must provide adequate facility for cross ventilation within the rooms by providing appropriate windows in terms of its position, in terms of its size. We have seen this strategy also in detail. Screened porches and patios can also provide comfort cooling by ventilation in warm weather and can prevent insect problems. Also, on hot days, ceiling fans or indoor air motion can make the rooms cooler by about 2.8 degrees centigrade or more. Thus, that will lessen the load on air conditioning. Then, open fan interiors can promote natural cross ventilation, or you can even use louvered windows which can direct the breeze as per your requirement. So, having louvers at inlet like this will direct the breeze downwards, and having the louvers in this direction will direct the breeze upward in the inlet. To produce stack ventilation, when speeds are low, maximum vertical height between air inlet and outlet in the form of open stairways, two-story spaces, roof monitors can also aid in ventilation. A whole house fan or natural ventilation can store nighttime coolth in high mass interior surfaces due to night flushing or reduce or eliminate air conditioning. So we have seen what is thermal mass, we have seen what is night flushing. That also to some extent can be used. Then for the month of March, this is one of the more comfortable climates. So shade to prevent overheating, open to breezes in summer, and use passive solar gain in winter will be a good strategy. And traditional passive homes in climate use lightweight construction with slab on grade and operable walls and shaded outdoor spaces, which is valid even for March climate in Chennai. Traditional passive homes in warm-humid climate use high ceiling and tall operable French windows protected by deep overhangs and verandas. Shaded outdoor buffer zones such as porch, patio, lanai oriented to the prevailing breezes can extend living and working areas in warm or humid weather. We must provide enough north glazing to balance daylighting and allow cross ventilation for at least about 5% of the floor area. Low pitched roof with wide overhangs, they work well during March period or Chennai climate. Then we can use plant materials like bushes, trees, ivy covered walls, especially on the west, to minimize heat gain. Summer rains support native plant growth. In wet climate, well ventilated attics with fixed roofs work well to shed rain and can be extended to entries, porches, verandas, outdoor work areas. If soil is moist, we can raise the building high above the ground to minimize dampness and maximize natural ventilation below the building. We can minimize or eliminate the west facing glazing to reduce summer and fall afternoon heat by using either vegetation which will cast its shadow or by having appropriate shading devices which will create a shadow on the western wall. Window overhangs can be designed or operable sunshades such as awnings that extend in summer can reduce or eliminate the load of air conditioning. So have extended awnings or have extended shading device. Use light colored building materials and cool roofs with high emissivity to minimize conducted heat gain, as cool roofs will reflect the solar radiation back, preventing it to be absorbed by the roof material. Then, in order to make 100% of the hours comfortable, what should we do? So far, what we saw what are the simple passive strategies that can be used in warm, humid climate for the month of March. Now, because of that, less than 50% of hours were comfortable based on all the strategies that I had told you. But we want 100% comfortable hours. For March, what should we do? For that, sun shading of windows, which is a simple passive technique, can be done. Adaptive comfort ventilation that can push by 47%. Active means such as fan forced ventilation cooling, dehumidification that pushes the comfort hours by 8%, fan forced cooling makes 8.3% hours comfortable, and cooling with the aid of dehumidification, which is basically air conditioning, will push the comfort hours of 44.2% from discomfort to comfort, and in this manner 100% of the hours can become comfortable by selecting these strategies. So all this which was initially red has now become green by adopting active strategies. So this is by adopting active, passive for March, for Chennai. So for this solstice, this is how we can shift. So what are these strategies? A whole house fan of natural ventilation can store nighttime cooling in high mass interior surfaces due to night flushing to reduce or eliminate air conditioning. We can orient most of the glass to the north, shaded by vertical fins in very hot climates, because there are essentially no passive solar needs. During March, we do not need any solar heat gain inside the building. Also, we can raise the indoor comfort thermostat set point to reduce air conditioning energy load or energy consumption, especially if occupants wear seasonally appropriate clothing. So instead of having the thermostat set at 22 degrees centigrade, we can set the thermostat at 26 degrees centigrade, provided the occupants wear climate responsive clothing. So if they wear light colored, light dressed material, say made of cotton, maybe cotton shorts and t-shirts, or cotton dresses, then the thermostat set point can become 26. Instead of someone wearing very heavy clothing like heavy jeans and jacket, then probably the thermostat temperature has to be lower. It can go even up to 22 degrees centigrade. But by doing that, there will be more energy consumption. Then in this climate, air conditioning will always be needed, but can be greatly reduced if building design minimizes overheating. So in hot humid climate, it is very difficult to push all 100% of the annual hours to comfortable zone without the aid of air conditioners, especially in the month of March. Then we will see what happens in the month of June. After, in 3 months, what is the shift that happens? When you use simple passive strategy, when you use simple passive strategy for the month of June for Chennai climate, which is warm and humid, what happens? 30.7% hours can be made comfortable just by sun shading of windows. Then 0.1% or just 1 hour can be shifted from discomfort to comfort by two-stage evaporative cooling. 33.2% of the hours can be made comfortable by adaptive comfort ventilation. In total, 33% of the hours can become comfortable by using simple passive strategies, whereas 67% will remain uncomfortable during the month of March. So, what are these strategies? Simple passive strategies, which can be adopted in the month of June for Chennai. So, good natural ventilation can reduce or eliminate air conditioning in warm weather if windows are well shaded and oriented to prevailing breezes. Then, next strategy is to facilitate cross ventilation by locating door and window openings on opposite sides of the building with larger opening facing upwind if possible. Then the next strategy is to have screened porches and patios that can provide passive comfort cooling by ventilation in warm weather and can prevent insect problems. Another strategy is on hot days, ceiling fans can reduce the indoor temperature by 2.8 degrees centigrade and thus the requirement for air conditioning can be reduced. Next strategy is to use an open plan interior so that you can promote cross ventilation, or you can use louvered openings which can direct the wind according to the direction of the louver. Then, in order to produce stack ventilation, even when wind speeds are low, we can maximize vertical height between air inlet and air outlet by means of open store wells, two-story spaces, and having roof monitors, clear stories, etc. The next strategy is to use a whole house fan or natural ventilation that can store nighttime cooling in high mass interior surfaces along with night flushing, thus reducing the load on air conditioning. Now, in order to shift 100% of the hours from uncomfortable to comfortable, that is shifting all these red dots to comfortable hours. So, this strategy 15 is the one which will shift the entire uncomfortable to become green, which is comfortable, and that 15 is primarily air conditioning. Cooling and dehumidification, if necessary, is air conditioning. So, in order to shift 100% of hours to comfortable in the month of June, 30.7% hours can be made comfortable by sun shading of windows, 0.1% can be made comfortable by two-stage evaporative cooling. 33.2% hours can be made comfortable by adaptive comfort ventilation. All these are simple passive strategies. Whereas 1.1% or 8 hours can be made comfortable by fan forced ventilation cooling, and which comes here in this zone, and then 66.7% can be made comfortable by air conditioning, that is active means, leading to 100% hours becoming comfortable for the month of June. 100% comfort hours for Chennai, which is a representative of warm humid climate. So how to further, while using these strategies, still try to be little more sustainable? That is possible by having a whole house fan or natural ventilation with high mass interior surfaces and having night flushing technique. The next strategy is to orient most of the glass to north with vertical fins as shading devices and having essentially no requirement for passive solar heat gain. Also, we can set the thermostat to a lower temperature, and that is how we can reduce the energy consumption. Also, in this climate, air conditioning is always needed, but we can greatly reduce it by building designs which will minimize overheating. Then we will see what happens for the month of September for Chennai. What are the simple and advanced passive strategies for hot humid climate of Chennai for the month of September? So what happens is 29.3% of the hours can be made comfortable in September by solar shading of windows. 0.1% or 1 hour can become comfortable by two-stage evaporative cooling. 56.8% of the hours can be made comfortable by adaptive comfort ventilation. So these three strategies are passive strategies. So just by adopting passive strategies, 57% of the total hours can become comfortable in the month of September with passive strategies alone. So what are these strategies? How do we achieve this? The first way to achieve is to use plant materials like bushes, trees, ivy covered walls, especially on the west, in order to minimize heat gains. If summer rains support native plant growth, nothing like that. We can even have moss walls. Then in wet climates, well-ventilated attics with pitched roofs work very well to shed rain and can be extended to protect entries, porches, verandas and outdoor work areas. The next way to achieve more comfort hours with the passive strategies is that if the soil is moist, then it is better to raise the building high above the ground to minimize the penetration of dampness into the building and to encourage breeze movement below the building. The next strategy is to minimize or eliminate the western sun by shading it either with shading devices or with vegetation. Window overhangs designed for this latitude or operable sunshades like awnings. These are natural sunshade. We can have awnings which will further prevent the solar radiation from hitting the wall or the glazing, thus reducing the load on air conditioners. So we can have awnings extended, and because of which the solar radiation does not strike the wall surface. We can use light building materials and cool roofs with high emissivity to minimize conducted heat gain, as cool roofs will reflect away solar radiation, allowing less heat to be absorbed by the roof. Then let us see what should be done in order to make 100% of the hours comfortable. 3 hours or 0.4% of the hours can become comfortable because of dehumidification, and 42.8% of the hours have to have air conditioning if you want the indoors to be comfortable for 100% of the hours. And so air conditioning is a must if you want 100% of the hours in September to become comfortable. Now let us see what are the ways in which we can still use this and make the buildings energy efficient and sustainable. So the first strategy is to use a whole house fan or natural ventilation, which involves high mass and night flushing, which can reduce or eliminate air conditioning. Then we should orient most of the glass to the north, shaded by vertical fins, because we do not need any solar gain in this climate and in this month. Further, we can lower the set point of the temperature on the air conditioner and save energy. Also, in this climate, air conditioning is always needed, but we can reduce it if we design building as a response to the climate. Now let us see what are the strategies that are required for the month of December. Now if you see for the month of December, the passive strategies that are needed, passive strategies for December are 26.5% of the total hours can become comfortable just by solar shading of windows. 0.3% or 2 hours can become comfortable by two-stage evaporative cooling, and 62.9% can become comfortable if we use adaptive comfort ventilation. So these three strategies put together accounts for 64% of the hours by which we can shift uncomfortable into the comfortable zone. So here we can shift 64% of the hours to be comfortable by adapting passive strategies. So what are these passive strategies that you need to adapt for the month of December? So this alone, I will not repeat it now because we have already seen this, how to use these strategies. Now let us see what to do if we need to shift this 64% to 100%. How can that happen? That can happen if we use dehumidification, because of which 25.1% of the hours get shifted to comfortable range. Fan forced cooling is another strategy which will shift 44% of the hours to comfort, and air conditioning requirement is only for 18% of the hours or 134 hours to shift from uncomfortable to comfortable. So in order to have 100% of the hours shifted from uncomfortable to comfortable, one needs to follow these three strategies for the month of December for Chennai. So how do we achieve these strategies? So the first is we can raise the building on stilts or pilotis if the soil is moist, and that will also enable the stagnant moist air to be removed by natural ventilation, and the whole house fan or natural ventilation can store the nighttime cooling with the help of a high mass and through night flushing to reduce the load on air conditioner. Now we have seen what are the simple passive strategies for 4 months or 4 solstice months of the year for Chennai in terms of just passive strategies, and in order to make the remaining hours also comfortable, what are the active strategies that also we have seen. Now let us compare how for each of these months what are the strategies that must be used. Now for the month of March, the comfort that is achieved using passive strategies alone is 48% of the hours can become comfortable. In June, only 33% of hours can become comfortable with passive strategies. In the month of September, 57% of the hours can become comfortable if we use passive strategies, whereas in December, 64% of the hours can become comfortable by using passive strategies. So what are these passive strategies? For throughout the year, sun shading of windows is mandatory. For these three solstice period, June to December, two-stage evaporative cooling can be a good strategy. Throughout the year, adaptive comfort ventilation, which is basically having openings of appropriate size, location, well shaded with proper shading device, is mandatory in order to make the remaining percentages also as comfortable. So in order to make the remaining 52% or 67% or 43% or 36% as comfortable, what should we do? We should adapt the active strategies. What are the active strategies? Throughout the year, fan forced ventilation can be used. Dehumidification alone can be used, except for the solstice in June. For all the months of the year, air conditioning for at least few hours is mandatory. So, this is how we will use climate consultant to understand what strategy must be used for which year. Now, once you use a particular strategy for 1 month, you can't demolish it for the next month. And therefore, it becomes very important for you as an architect to understand which strategy will get more importance. With the help of the psychrometric chart and climate consultant, which helps us to understand how many hours can be pushed from uncomfortable to comfortable hours, we can decide which strategy must be adopted in that building. So next we will see some other aspects of how to design in warm humid climate. So let us look at the design considerations in detail. So warm and humid climates are characterized by high temperature and high levels of humidity throughout the year. This climate type, which is found in the tropics, is also a place which has more population. Hence, it's important for us to understand how to design in this climate type, as it will benefit a large number of population. Frequent rainfall is also common characteristics of this climate, and in some locations it rains almost every day. These conditions also create a good ambience for insects and moss to grow. So, while deciding on building massing and spatial configuration in the warm humid climate, we must consider two important things. First is the reduction of solar exposure on the building envelope. This helps in managing solar heat gain through the building envelope, which is walls, roofs and windows. Second is utilization of wind flow to ventilate internal spaces in order to evacuate heat and provide thermal comfort to the occupants. The main building envelope features that influence daylighting in residential units are the size and location of window openings is very important. We have seen this as one class previously, as one lecture in this course. Shading systems for windows, again this we have seen as one lecture in this course. Window glazing with light transmission properties. We have seen this also as one of the lectures. Color and finish of nearby surfaces. So, nearby surfaces, the color and finish is important because this climate type is in the tropics, and tropics can at some times give very harsh lighting, and if it is reflected from adjacent surfaces, then it can be very harsh to the eye and also glare can happen. Color of internal surfaces is important. The building envelope design should aim at achieving reduction in cooling thermal energy demand, improvement in thermal comfort, and provision of adequate daylighting in typical spaces such as bedroom, living room, and kitchen. Let us look at the simple passive strategies to be used in this climate. The first is building envelope form and orientation. East-west axis orientation with the longer facade facing north reduces solar heat gain from east and the west facades. Buffer spaces like service core, toilets, etc. should be placed along the east and west and also sometimes along the south direction to minimize heat gain. So, you should provide staircases, lifts along east or west. Envelope in these regions should be well insulated with low thermal transmittance value or low U value. With increase in volume, building envelope heat gain and heat also increases. So, when you design these buildings, you ensure that you buffer the east and the west well. With increase in volume and building envelope, heat gain also increases. So, compact planning with smaller volume of the exposed area reduces heat gain from the building. Rectangular plan form is beneficial with longer facades in north and south direction to reduce heat gain from shorter sides in east and west direction. But the best would be to go for a square plan. If at all it's a rectangular plan, then ensure that the east and west has the shorter side while the north and south has the longer side exposed. Second is walls. Most exposed surface in the building envelope is the wall. Low thermal transmittance or U value materials for walls is preferred. Lightweight construction materials for walls must be preferable. Outer surface of the wall should be shaded, light in color and should be reflective as much as possible. Methods like cavity wall, thermal mass, external reflective materials, and light colored finishes are preferable. Thermal mass plays an important role in maintaining thermal comfort inside the building for occupants. These are very generic. Even in hot and humid climate, in some places it is better to play with light walls and some places it is better to play with the thermal mass. Third is windows. Now, the window to wall ratio of 20 to 40% as per ECBC is required to avoid glare and overheating. When it comes to windows or fenestration, low U value with low solar heat gain coefficient to minimize heat transfer into building is preferable. Use of double or triple pane glass with low E value is encouraged. Low thermal transmittance glazing technologies such as electrochromic or thermal electrochromic, which is thermoelectrochromic, and reflective glazing is also preferable. When it comes to ventilation and position of openings, building openings must be towards the windward side. Normally, because it's a coastal place, in places like Chennai, the direction is south and southeast. Courtyards can be provided so that warm air gets risen and cool air from ground floor flows into the building. Wind tower can be used as a passive strategy to provide ventilation. Solar chimneys enhance ventilation because of the stack effect. In warm, humid regions, openings should be designed to capture wind as ventilation is the key comfort defining criteria throughout the day in this climate. Having openings which direct the wind upwards is not a good idea because in the working zone there will be no ventilation. Hence, it is better to avoid louvers or opening which direct wind towards the ceiling. It is better to have sashes which direct the wind towards the working level, or we could even have louvers which direct winds towards the working level. The living zone is the space commonly used by occupants and air movement should be directed through this space. The sizes of the openings can be larger and closer to the floor for maximum comfort. They should be placed along the windward side to make sure air moves in and out of the building freely. Therefore, regardless of the place, natural cross ventilation in building is as essential as breathing is to humans. Otherwise, the sweat that forms due to high humidity makes it very sticky and uncomfortable, especially in the combination of high air temperature. So, a typical plan of stacking rooms one behind the other must be avoided, whereas a courtyard should be introduced in the plan. This can help in bringing more natural light as well as in ventilation, facilitating ventilation. They also ensure that properly designed openings can be given to enhance cross ventilation in the houses. Fifth is shading. Shading reduces the solar heat gain through openings, as it also reduces the mechanical cooling demands inside the building. The sun is at higher elevations during summer and lower in winters in the southern direction. So, shading devices on southern fenestration only allows low angle sun paths for winters and penetrate higher solar radiation in summers, while shading devices on north fenestration are only meant to block higher sun angle during summers. North and south facades can be protected by overhangs. East and west direction needs special shading devices like louvers. The southern facade requires only horizontal shading devices such as this and strategies to penetrate solar radiation, whereas east and west direction requires special shading devices to penetrate extreme solar radiation. So, egg-grade shading devices are helpful along the east and the west direction. Sixth is landscaping and positioning of trees. Shading of exposed surfaces reduces direct sunlight and prevents heating of surfaces. Shading of open ground in sight is important, and shading of horizontal or vertical surfaces like green walls is also important. So, green walls can act as a shading of vertical surfaces. Roof gardens or green roofs or even cool roofs are encouraged. There must be buffer against hot winds, and direct solar radiation and glare must be blocked with the help of landscaping. Deciduous vines covering the wide trellis on the north and south side of a building acts as shading devices. These can provide comfortable outdoor areas and solar protection. Plant species that allow penetration of low angle winter sun have to be used for shading the building and its outer surfaces. Evergreen trees with high canopy can be used on the east and west side of the building to improve its solar protection in the morning and afternoon. These trees allow the movement of air underneath the canopies. Certain species of tree such as Samana samane, also commonly called as the rain tree, forms an extraordinary outdoor space by creating a huge canopy effect. They should not be planted too far from each other so that the crowns form a wide hall-like space, creating a comfortable microclimate. Buildings should be separated with large free spaces between them. This allows airflow, which provides ventilation for cooling and a hygienic environment. An unshaded pavement should be avoided as far as possible, and air should not be allowed to pass over such surfaces before reaching the buildings. Low vegetation and bushes, however, should be avoided near the buildings because the space between the ground vegetation and the high crown of the trees should remain open, providing free access for the wind at the level of the living spaces and also prevents dampness. The next criteria is to have a green roof. Green roofs are excellent in providing water retention or stormwater drainage. Water retention, as we had seen when we discussed green roofs, it provides green space, provides improved water and air quality, energy consumption is reduced, it insulates the roof, provides ambient air temperature reduction, it alleviates pressure on the sewer system, it protects the roofing membrane, it reduces noise and filters pollutants. Next is the roof. Roof is the area from where maximum solar radiation and heat enters the house in a hot and humid climate. Cool roofs are a good option under such circumstances. Cool roofs are basically roofs that are painted in light color shades or have reflecting material coating so that it reflects most of the solar radiation and reduces the thermal heat gain. As per some studies, it is seen that conventional roofs reach about 60 degrees centigrade temperature in summer, whereas cool roofs stay at 28 degrees centigrade, than, which is much cooler than the conventional roofs. Low thermal transmittance U value roof construction can be used to reduce heat gain from roof assembly. Solar panels or rooftop building integrated photovoltaic system can also act as a second skin on roof to provide shade, which can also reduce solar heat gain through the roof assembly. So, in hot climates and climates with hot summer, a light colored roof reflects sunlight, remains cooler, and offsets carbon dioxide warming and reduces the amount of heat transferred to the interior of a building. Cool roofs have surfaces that reflect sunlight and emit or discharge heat efficiently, keeping them cooler on sunny days. The two surface properties that determine a roof's temperature are solar reflectance and thermal emittance, which range on a scale from 0 to 1. The larger the two values are, the cooler the roof will be. The roof surface should be a light color and roofing material that has a surface with solar reflectance of more than 0.7 and thermal emittance of more than 0.75. In hot climates, cool roofs can help to mitigate urban heat island effects, reflect solar radiation back to space, and keep the indoor spaces comfortable. Next is the double roof. Now, in hot climates, the structure located just above the roof shades the roof and allows warm air buildup between the roof and the structure to escape. In hot climates, direct sunlight is the largest contributor to building cooling loads. Because a roof receives the most direct sunlight over the day, a double roof or shade structure above the roof will reduce the cooling requirements. In hot climates, incorporate a double roof structure separated by an air cavity and extend the roof line to shade exterior walls and create shaded outdoor living spaces. Use cross ventilation or ridge vents to ventilate the air cavity between the roofs. A double roof structure located high above a roof can also provide shading for an outdoor roof garden or terrace. Next is cooling. So, you can have thermal mass cooling, that is, thermal mass regulates the space temperature by controlling stored thermal energy in the buildings. Heavy thermal mass buildings maintain comfort even after the HVAC is shut down. It delays heat ingress combined with natural ventilation and night purge, which ensures natural pre-cooling. In warm, humid climates, low thermal mass buildings prevent heat buildup and dissipate it quickly. If we look at radiant cooling, conventional air conditioning relies on convection and radiant system to use radiation for heat transfer. Radiant systems often combine with thermal mass and maintain comfort by absorbing and radiating heat. Coils in floors for heating and ceilings for cooling optimize radiant system performance. Radiant cooling systems include chilled slabs and ceiling panels offering different cost and performance benefits. Next is dehumidification or desiccant cooling system. A desiccant is a substance that absorbs water from air to dehumidify it, later releasing the moisture when heated in a continuous cycle. Desiccant systems are categorized into open and closed systems depending on whether the desiccant directly contacts air. Solid desiccant systems use materials like silica gel or zeolite, while liquid desiccant systems utilize substances like lithium chloride or calcium chloride. Desiccant systems are effective in regions with low heating demand but have limited application in high humidity areas, with ongoing research in India to enhance their viability. Normally, if desiccants are used, then they are used in combination with the air conditioning system, because the act of removing moisture from the air by the desiccant is an exothermic reaction and it gives out heat, further increasing the temperature of the surrounding air. And last but not the least, we will look at the lighting. The activity zone is important for daylighting distribution. Areas which require same amount of lighting can be placed adjacent to each other. Daylighting areas are divided into three zones, which are fully lit, partially lit and non-daylit areas. Less artificial lighting reduces the internal heat gain in the building. Side lighting and top lighting can be used for natural light without allowing direct sun rays to penetrate into the building. Top lighting is effective for the spaces which are directly below the roof, and side lighting blocks the direct sunbeam and provides a glare-free light into the building. In this technique, direct sun rays are reflected towards the ceiling, after which it provides diffuse light throughout the area. We will look at case studies of buildings in warm and humid climate where some or most of these techniques have been applied. The first case study that we would take is the Arcot Plaza. The Arcot Plaza is a commercial building, an award-winning one, located at Chennai. It is designed by architect V.S. Vigneshwar of Architecture Plus Value. Now, this building is located on a very busy transportation corridor. The ground plane is extended as a public plaza which connects the double height retail to the street. The office floors above are capped with green terraces. The design idea was to maximize the visibility of the building and tap the potential in terms of footfall, as the site is located between the existing railway station and an upcoming metro station. The ground plane is designed as a public zone. The front edge of the site is designed as a public plaza, extending the sidewalk into the site, with the building having a inviting double height atrium for the retail branch. The office floors have a separate entrance lobby at the rear with a vehicular drop-off. The top floor is designed as a premium office with a large terrace garden which cuts the heat load of the office. If we look at the conscious design decisions taken, the form of the building was a direct response to the climate. The northern side faces the street and care is taken to protect the glass frontage of the building with appropriate and innovative shading devices, thereby providing effective daylighting and reducing the solar heat gain on the building. The retail facade is protected by the office floors cantilevering from above. The western and eastern side have been designed with appropriate openings to facilitate cross ventilation inside. This building has north light louvers in order to get constant daylight without glare along the north side, which is its front facade. The eastern openings on the other side have larger openings with sunshade to allow more daylight. There are large overhangs that protect the glass from direct sunlight. The glass on the north side is protected by this large overhang. So, the built form is a response to the climate, the context, and the function of the building. The building also has a service core which is positioned on the south. So, this is positioned on the south as it minimizes the building's heat. On the west side are smaller slit windows. So, these are small slit windows with adequate sunshade to prevent the harsh west light but allow the southwest wind to enter. Also, if you look at the site and the design context, you can see that there is a public plaza in front, and this facade offers maximum visibility with a glass but yet has adequate shading provided at higher level. Here you can see how each of the facade has been treated. The north side has north light louvers which gives continuous daylight without glare. The western side has small slit openings which are well shaded, through which the southwest winds can go in, and yet the harsh sunlight is cut off. The eastern side has large openings or more openings than the western side, and it allows daylight. Southern side has minimum openings. The openings are very minimal on the southern side, and it minimizes the building's heat gain. The building also has a green roof partially on top. The form of the building is a direct response to the climate. As the north side faces the street, care is taken to protect the glass frontage of the building with appropriate and innovative shading devices. Now, if you see, on the east are operable windows, and the openings can be angled based on the solar direction, sun's direction, and wind direction. Similarly, along the west, the slit windows in random patterns protect the inside from harsh sunlight, and it also has adequate shading, and the operable windows can also be turned towards the direction of the wind. So, care is taken to protect the glass frontage of the building with appropriate and innovative shading devices, thereby providing effective daylighting and also reducing the solar heat gain on the building. The retail facade is protected by the office floors cantilevering from above. The west and the east side has been designed with openings that facilitate cross ventilation inside. Let us now look at the north opening. On the western side, in Chennai during summers, the setting sun moves northward. During such months, the fins provide diffused light. During other times, they cut the glare from the bright sky. It also offers an interesting view of the street from the office spaces, breaking the monotony of the spaces. Also, the glass used is solar rated glass to cut heat gain. Let us now look at the north facade. Now, innovative daylighting facade has been adopted here. The northern facade of the building for the office floors was designed to give glare-free daylighting for the workspaces. The triangulated translucent polycarbonate fins placed in carefully determined patterns cuts the direct sunlight. To cut off excessive solar heat falling on the glass and the associated glare, the architect has structured the shading devices in the form of triangulated translucent polycarbonated fins in a designed pattern. The fins projecting perpendicular to the facade. Some of the design objectives achieved through this project are: maximize site visibility by creating a public plaza and an iconic form. Creation of an iconic building with the lowest possible budget. Natural light without glare for office spaces. Solar passive design with appropriate shading features. Climate responsive design with lower heat gain. Maximum visibility for retail spaces with higher footfalls. And achieve maximum revenue. So, the northern facade of the building for the office floor was designed with an outer stainless steel frame and a polycarbonate sheet attached to it. Now, these provide glare-free natural lighting, and you can see that there is adequate natural daylight on the workstation as well as in the conference hall. So, this is the north side and the west side view. So, continuing with the glass frontage of the ground and mezzanine floors for the rest of the floors rather than the concrete facade overlaid by heat trapping panels, the architect has given the street facing side of this building a solar rated glass frontage. With this, cost-free daylighting for the workspace has been achieved. Chennai being a city where heat and light are in surplus, it really works and helps. At night, when everything is lit up, the fins reflect the interior lighting of the building in various geometric patterns. Now, let us look at the second case study. The second case study is the REC Tech Park at Tandalam, Chennai, again by architect V.S. Vigneshwar of Architecture Plus Value. So, here in this building, the client had requested to develop a tech park within an REC campus for computer science engineering students training and startup incubation. So, the Rajalakshmi Engineering College wanted to have their own tech park. It was aimed to encourage recent graduates to enter the startup ecosystem. The requirement was that the building must be completed fast within 180 days. An innovative and futuristic design at the campus entrance must be available to be seen. The concept of the tech park was to provide space for training, socializing and starting up. Learning extend beyond classrooms into non-program spaces to foster innovation. The design features achieved include sustainable and cost-effective glass facade, maximized natural light and ventilation, vibrant colors and materials to enhance creativity, climate friendly design considering solar orientation, social spaces for student interaction, efficient space planning with zero wastage, context responsive architectural design, and iconic building created cost effectively and to be completed with steel or dry construction within 180 days. The design process mainly had the site and climate influencing the design decisions. There was an atrium which is designed for natural light and ventilation. So, some of the tangible aims which were achieved through this design are designing a sustainable and cost effective glass facade based building, provision of maximum natural light and ventilation for all the areas through careful design of the facade and roof, use of color and materials to bring vibrancy and a sense of identity to the tech park that helps to create a startup friendly atmosphere and enhances creativity. Some of the passive features used are a thorough analysis of the climate, wind flows from southwest, northeast, reflecting glass and panels were used, double skinned wall has been used, clear story lighting has been used here along with the double skinned wall. With an understanding to the climate, this building was designed in a climate friendly manner. Each side of the building is designed to respond to climate and solar orientation. The facade detailing is done in such a way as to bring in constant reflected natural light without glare. There is provision of social spaces in all the common areas of the building to enhance the interaction between students and provide breaks in the non-programmatic areas. These were done through providing seating areas, green spaces and natural light pockets within the building atrium and outside the building in the setbacks. Efficient planning in use of all built and unbuilt areas have been done. The circulation and program spaces are designed with zero space wastage, responding to the context and creating an identity for the center through sound architectural design. A iconic building is created in a cost-effective manner. Use of complete steel or dry construction enables the building to be completed within the stipulated 180 days. The most influencing factor in this design is the site and the climate. The north side has the administrative entrance. This side also has many trees and a good green cover. The south side has a playground and this acts as a student entrance. The atrium was conceived as a playful space that bridges both these areas. The atriums were designed to be naturally lit and ventilated. Thus, the cost of lighting and ventilating a large space was cut off. The roof of the atrium is made up of translucent polycarbonate sheets that allow natural light into the atrium. This in turn leads to reflected glare-free light inside the classrooms and programmatic areas. The natural ventilation is aided in the atrium through the operable facade on the north and south side of the atrium. The vegetation on the north and the playground on the south lead to a pressure differential allowing for constant air movement in the atrium, which creates a pleasant environment inside. Structural steel skeleton with insulated boards have been used. The atrium facade with operable glass windows for ventilation. North and south facades with solar rated mirror glass and wooden HPL sheets have been used. Double skin on classroom facades have been used to reduce heat. Subtle interior colors reflecting nature has been used for psychological appeal. The construction system was an innovative system of a structural steel skeleton with a decking sheet floor system. The sides were clad with insulated boards and the roof of the building was designed with polyurethane foam sheet. The atrium facade was detailed with operable glass openings allowing natural ventilation throughout the building. The north and south facade were detailed with solar rated mirror glass interspersed with wooden HPL sheets. They reflect and mimic the natural surroundings and enhances the presence of the building, giving a futuristic feel to the project. The classrooms and the programmatic spaces were organized on the east and west sides. These facades of the classroom had an external double skin which cuts the heat. The AAC wall with openable windows were covered with a MS structure mounted with louvers to cut down the heat and glare. Also, the services were allocated between the two skins, which provided an additional thermal buffer and provides a way to conceal the otherwise ugly and visible service lines in the building. Here you can see on the north and south facades were detailed with solar rated mirror glass interspersed with wooden HPL sheets, with the facade having a structural steel skeleton with insulated boards. The atrium facade with operable glass openings for ventilation was present. The north and the south facades had solar rated mirror glass and wooden HPL sheets. Double skin was used on classroom facades to reduce its heat, and subtle interior colors reflecting nature for psychological appeal. So, in today's class, we saw two case studies from a typically hot and humid, though it is classified as warm and humid zone. We have seen two case studies from Chennai, which have been designed with some climate consciousness and as a response to the climate. With this, we will stop today's class and we will continue next class by looking at the strategies for hot and dry climate. Until then, thank you.